So now what I need to do to get this derivative, I need dy dx. I want to know how this dependent variable is related to this independent variable. I don't know that rate of change. I don't care how it's related to the intermediate u function necessarily, right? I need to know it, but that's not really what I would want to get at. So dy dx is going to be dy du. Okay, so what's dy du? What's the derivative of sine? It's going to be cos u, right? That's the only way it's the other way, right? So cos u. So I need dy du times du dx. So I just wrote above. So dy du, you just told me that's cos u. So I'd have cos u times du dx. What's du dx? What's the derivative of a quarter x? Don't let these little expressions fool you. Yeah.
Is it 1/4?
Yeah. Don't play a quotient rule on it, and you don't have to. This is just 1/4 times. It's a constant times x, right? 1/4 times x, so it's a quarter. So times a quarter, right? This is that one, and this expression is that one, right? But I don't want the expression in terms of u. I want it in terms of x. So I should replace u with the function of x that it really is. So it would read cos x on 4 times a quarter. Right? Yeah.
This is the same as u substitution, or
The u substitution is going backwards. The way to think about u substitution, you saying for integrals? The way you should think about u substitution is undoing chain rule.
Okay.
Every integral undoes a derivative, right?
Yeah.
So how do you undo a chain rule derivative is by u substitution.
Okay.
So that's why it looks so similar.
Okay.
Yeah. U substitution is the backwards end of this one. Are we okay with this notation? I think we'll do u substitution in this class even, right? I think it's like the very last section maybe. This is exciting. Try one more with this particular notation. Number 13, secant e to the x. Again, we haven't done any 3-link chains yet, correct? Or 2-link chains. Again, it can get extremely complicated. You have to really pay attention to the flow. Secant, and inside the secant is e to the x. So if I write this in terms of y as a function of u, so y equals secant u, and that means that u, this intermediate function, the inner function, is e to the x. So dy dx will be the derivative of y with respect to u. So that will now look like the standard derivative. The derivative of secant is secant tan. Oops. Yeah, that's what it was. Equals dy du times du dx. So the dy du is secant u tan u. And you multiply that by du dx. Well, that's just itself again, right? Du dx is e to the x back. So times e to the x. But I don't want to have the expression in terms of u, I want it in terms of x values. So I now replace the u's that I have in this expression with e to the x again. So it reads e to the x, I'm moving this e to the x to the front, and it reads secant e to the x tan e to the x. Any questions? So I'd like to pick a harder one here in a second.
dy equals secant u.
dy du is secant u, that's correct. But at the end I replace the u's with the function it really is.
But dy du is secant
dy du, yeah, dy du is secant u tan u. You know what I said, or did I say something?
derivative of secant.
Correct. dy du is the derivative of this variable with respect to that variable. Use the variable you want. So you had w, or omega, equals sine phi. No, it's not phi. Sorry, lose a phi. Phi. So you had that. So I want to find the derivative. Well, the standard derivative in this case would be d omega d phi. So what's that going to be? Cos phi.
So that are
The derivative of dependent with respect to independent. That's what the notation is meant to describe. In almost all our contexts, it's always y's and x's, right? Or df, dx, things like that. It's always dependent with respect to independent. So here, once you write this as u is seen as the independent variable here. It is more complex, right? U is really another function of x. But for the moment, y in terms of u, its derivative is secant u tan u. Then you replace the u in a second with e to the x. Look at the derivative of what?
Look for the derivative of y, dy, which is secant q.
I'm looking for the overall. I'm looking for the derivative of y with respect to x. But because this function is put inside this one, so there's this intermediate stage that I have, this dy du, because I'm going to multiply them together to get the overall derivative. So when I replace u instead of e to the x, I can take a standard derivative. I don't have to resort to chain rule on this little guy right here. I just want dy du, that is this intermediate step in a sense. And multiplying that by du dx gives me the overall derivative. Which is why it's called a chain. I'm forced to go through this inner function to get to the derivative of the entirety of this composition. This is not the standard way you're going to take these derivatives, though. Okay? But this is the way the book describes it when they refer to version 1 and version 2. I'll try to do a more complicated scenario, and I'll show you how you do it in general. Oh, there's nothing more complicated. That's horrible. Oh, there we go. That's a good one. 41. 41 is a good example. 41 is tan of e to the root of 3x. There's our function. So a person has to first realize how many compositions are going on within a particular expression. 3? Blue, did you say 3?
There's 3 in total.
There are 2 compositions and 3 functions. 3 functions. Well, I mean, you're correct. Yeah, there are 3 functions, and they're composed with 2 compositions, right? The root of 3x has been put inside the e to the x function, and then that expression has been put inside the tan function. Okay. With me so far? Blue, didn't you wear that shirt yesterday? Me too. All right. Yeah. That's really Oscar the Grouch. That's all. All right. Anyway. Yeah, sure. So let's see here. So dy dx we want to get to. So what I need to first do is take the derivative of the most outer function. What is the most outer function?
Tan.
What's the derivative of tan?
Secant squared.
Good. So we need a secant squared here. What goes inside the secant squared? Whatever is in there already. Whatever's inside the tan, right? Okay. So we keep that the same.